Hello and welcome back to another episode of Math with Zone. Today I wanted to take a quick video and talk about gravitational potential energy in terms of centrifugal acceleration and all sorts of other things to really get into the idea of dealing with these in terms of what would happen if you took the gravitational formula, the force for gravity, and you related it to an object that is trying to leave the Earth or leave a planet, okay? In order to do that, you would have to essentially have a force that was able to beat the gravitational potential energy, but that gravitational potential energy would be changing, all right? So what we have here is a little diagram. We got, imagine a ball or anything that you wanted to like kick or move or shoot off into the earth, out of the way, out of the earth. How much would it have to like initially have to leave this gravitational well? Well, in the beginning, the gravitational force would be really high. But as you get really higher, it would have less and less gravitational impact. It would have a whole lot more gravitational potential energy. But essentially what we want to do is mimic that and match the kinetic energy with the potential energy to see what would be the escape velocity. All right, so what we have here is the gravitational potential energy in relationship to the gravity formula, which at first confused me. But remember that gravitational potential energy is equal to mgh. All right? So the mass of the object, that's this m. Gravity, which is typically thought of in terms of like just 10 meters per second, times height. All right? And the thing that was confusing me was, where did this second r come from? And that's the height when you think about it. Because the second r, that r is changing, and it's really what would be like how far away do you have to go before you are escaping, okay? So that's the height. That's how I interpreted it. I don't know if it's right, but that's how I interpreted it to make it make more sense for me. So not really an AP Physics thing, but it is a curiosity thing. The escape velocity of an object is going to be taking an enormous amount of energy, all right? So with that in mind, the escape velocity is going to have this formula right here, the gmmr. We want that escape velocity to equal our kinetic energy that we would have. So we would need this negative gmmr. That would have to be equal to our negative 1/2, oh boy, 1/2 mv squared. And that is due to the fact that if we were kicking an object or trying to move something out of the earth, and if we had no extra acceleration added, how fast would it have to be going? Well, the masses are going to cancel. Not the mass of Earth, but the mass of the object, which makes sense because it's not really significant anyways. We would have a negative gravitational constant times the mass of Earth divided by the radius would have to equal a negative 1/2 v squared. They're negative because they're pulling downward. And then we would divide by negative, multiply by 2, and square root. All that math you end up with dividing by negative 1/2 ends up being 2 gravitational constant times the mass of Earth. Let's do an ME there. Divided by the radius. Square root would equal the escape velocity, which I considered kind of cool. And I even considered it even cooler because you could plug in some stuff here. If you plugged in the numbers, calculate the actual velocity, you could do 2 times the gravitational constant times the mass of Earth divided by the radius of Earth, and then you would end up with the value for the escape velocity, okay? So with that in mind, think about that for a second. In order to escape, if you wanted to leave the Earth's surface or Earth's gravity well, which is really just a neat topic in general, you would have to go 11 kilometers per second when you left the ground. When you left the ground, that initial upward velocity would have to be 11 kilometers per second. That is really, really fast, okay? It is 11,115 meters per second. So, like, you would blink and whatever you were looking at would just be gone. It would be outside the atmosphere almost instantaneously. It would have to be going that fast. Which is why when you see Earth's like rocket ships go up and whatnot, they have those flames for a while when you have a rocket. Those flames are on for a very long time. That's the worst looking rocket ever, to be able to leave Earth's atmosphere, because otherwise they would never make it. They have to constantly accelerate and get to faster and faster speeds. They don't have to get to this 11 kilometers per second by the time they leave Earth's atmosphere, but they do have to continue to accelerate to be able to get out. They have to make the radius a little bit further away, because the further away you get, the less that gravitational energy would be affecting you. All right, that's going to do it for this one. It was just an interesting one. I wasn't really sure if I wanted to do the video because it doesn't really relate to AP Physics too much, but it is kind of cool. All right, see you later.